Everyone, welcome back to the channel. If you're into data science and machine learning, then you're in for a treat today because we are going to dive into fascinating dimension reduction technique called random projection. Now, dimension reduction is one of those things that really comes in handy when working with high dimensional data. Data with ton of features, whether you're dealing with image, text, or any other form of high dimensional data. Reducing the number of dimensions while preserving the structure is crucial. But why random projection? Well, it's a simple yet powerful technique to reduce the complexity of your dataset without losing too much information. And the best part, it's computationally efficient. Now, in today's video, we are going to break down how random projection works with a real world complex dataset, and we'll even code it together in Python. So stick around, let's dive in. So let's start with the basic. Uh, what is random projection? So random projection is a technique where you project your high dimension data onto a lower dimension subspace using random matrix. And the key idea is that despite the randomness, this preserves the distance between the points reasonably well. And thanks to something called Johnson-Lindenstrauss Lemma. So this lemma tells us that for any set of a point in high dimension space, we can map them to a lower dimension space, such as that the pair distance between the point are accurately preserved. Right, pretty cool, right? And essentially, it is the way to keep the data structure intact while reducing the number of dimension. And when you make a subsequent machine learning model, this makes a subsequent machine learning model run faster and be easier to interpret. And you might be asking, why not use PC or TSNE? Well, random prediction has a few distinct advantages. First of all, it much faster, especially with really high dimension data. Unlike PC, which involves metric decomposition, random projection just require multiplication with random matrix, making it computational less expensive. And another benefit is the random projection works well with the sparse data. A data that has a lot of zeros or missing values, which is common in the field like natural language processing and recommender system. All right, now let's get our hand dirty with some code. We are going to use some complex data set for this, or 20 years group data set. It has collection of around 20,000 newsgroup documents, and it's a great example of high dimensional text dataset. First, we'll import the necessary libraries. We'll use scikit-learn for the random projection and PCA and the matplotlib for visualization. We'll also load the 20 newsgroup dataset, which has been pre-processed into document meta matrix, perfect for our example. So this dataset is already vectorized, meaning each document is represented at a smart matrix of word count, and the shape of the dataset is 18,000, which is we have nearly 20,000 documents, so over 13 130 features, and that's a lot of dimensions. Now let's apply the random projection. We have two common type, the Gaussian random projection and sparse random projection. So different is that Gaussian uses the tent matrix with random Gaussian value, while sparse uses the sparse matrix, which can be more efficient for a large data set. Here we are reducing the data to 50 dimension after applying the transformation. The new shape is 18,084.6 and 50, which is much more manageable. And now let's visualize the data. So we use the SNE to project it down to 2 dimensions just for visual purpose, right? And it takes quite a while to get processed. That's why I'm not running the cell in this video right now. Here's the visualization of our data after applying the random projection, and we have color coded the point based on their newspaper category. As you can see, even in 2D space, we can still see some cluster, which suggests that random projection preserve some of the relationship between the documents. And now let's compare this with PCA, which is another dimension reduction method to see how they differ. So in this code, we run PCA and we visualize the data using TSNE. We can see the similar cluster pattern, but notice the PCA visualization might look a bit smoother and more well defined in some areas, right? And however, PCA is generally computational expensive, especially for the large data set like this. So there you have it. The random projection is a powerful, fast, and efficient method for reducing the dimensionality of high dimension data set. It may not always preserve the data structure as well as PCA, but for many application, it's a great choice. Give it a try with your own data set and see how it's performed. And as always, don't forget to hit that like button. Thank you for watching, and I will see you in the next one.